In section 6.5, we are now finding probabilities using the central limit theorem, and oftentimes we're looking for the probability that the sample mean is less than or greater than a certain number. So if we look at number 16 in 6.5, it says let X be a random variable that represents white blood cell count per cubic milliliter of whole blood. Assume that X has a distribution that is approximately normal with mu of 7,500 and an estimated standard deviation to be 1,750. The test result of X is less than 3,500 is an indication of leukopenia. This indicates bone marrow depression that may be the result of a viral infection. Okay, so in part A, it says what is the probability that on a single test, X is less than 3,500? So this is the same type of problem we have been doing in section 6.3. So we're looking for the probability that it's less than 3,500. We know that mu is 7,500 and sigma is 1,750. So I know my mean is right here, 7,500. That means 3,500 is somewhere over here, right? So the area under the curve that I'm looking for is less than or to the left of 3,500. I'm just going to use the calculator and use my normal CDF. Remember, it's the lower bound of the shaded area, then comma the upper bound. So the lower bound goes all the way to negative infinity. So I do negative 1e99. Upper bound is 3,500. Mu is 7,500. And sigma is 1,750. I ran out of room a little bit there. So if we do that on our calculator, second vars, normal CDF. Remember when you type in the negative 1e99 to go down here to your negative 1, and then e is above the comma key. So negative 1e99, comma, 3,500, comma, 7,500, comma, 1,750. So we get 0.0111. Okay? So as a percent, that's a 1% chance that someone has the blood cell count less than 3,500. Okay, and part B, the difference in part B now says, suppose a doctor uses the average of two tests taken about a week apart. What can we say about the probability distribution of X bar? What is the probability of X bar? Okay, because the underlying distribution is approximately normal, the central limit theorem tells us the distribution of X bar is normal if one of two things happens. Either the underlying distribution is normal or our sample size is larger than 30. We have a sample of 2 here. But our underlying distribution is normal. Therefore, we can say that the probability distribution of X bar is also a normal distribution. What is the probability that X bar is less than 3,500? So that's the difference between part A and B. Part A is just the probability that X is less than 3,500. Part B is probably that X bar is less than 3,500. So what happens about the normal, since we know the X bar distribution is also normally distributed with the same mean, we know our mean is also 3,500. Remember the standard deviation of X bar then is the standard deviation of the original distribution divided by the square root of n. In this case it was a test of 2, so the square root of 2. So when we put it in our calculator, we're going to do the exact same thing. Normal CDF, same lower bound, same upper bound. I'm going to go to the second line, then comma mu. But when we put in our standard deviation here, in your calculator you can divide by the square root of 2 right here so that you don't have any rounding errors. So to bring up the last thing I typed in on my calculator, I'm going to hit second enter. And now it allows me to type at the end, and I do divided by 2. Whoops, not 2. square root of 2. Okay? That's the only thing we have to do different here. So now you see we have this e negative 4. Remember what e means, times 10 to the negative 4. So I'm going to have to move my decimal 4 places to the left, which would give me 0.0006. Okay? Part C, we're going to repeat it. Now our n will be 3. And then we can interpret it in part D.